Flux is given by the expression E delta S cos theta, where E is the electric field. Phi is equal to, according to the statement, 1 by epsilon naught times the total charge enclosed by the closed surface, as in this picture. The direction of the area is always normal and outward, and it is represented as n cap. Hello everyone, I am Maitri, Faculty of Physics, Vidhyaashram, Temple of Excellence. In this session, we will discuss the electric flux, Gauss law and its application. So let me start the session with the topic electric flux. What is an electric flux? Electric flux, to understand this, consider an area A. Through this area, number of field lines pass. That total number of electric field lines passing through the surface area, and that surface area must be perpendicular to the direction of electric field lines, is known as electric flux. And what is the symbol of electric flux? Phi is the symbol of electric flux. This electric flux is a scalar quantity whose SI unit is Newton per Coulomb meter square. So how this SI unit? Let us understand by the expression for the flux. So flux is given by the expression E delta S cos theta, where E is the electric field. E is the electric field and delta S is the area element of the surface S. Then the expression for the flux is, if I consider the small area, then the flux is also small, which is represented by delta phi, which is equal to E delta S cos theta. As we have cos theta in the expression, then the flux must be represented by the dot product. So flux is the dot product of electric field and the area, as it is a scalar quantity. So you know what is the electric flux? Electric flux is the total number of field lines passing through the area, and area must be perpendicular to the electric field lines, and flux is a scalar quantity which is given by the expression E dot, that represents the dot product of electric field and the area. When it is a dot product, then we can represent it as a delta phi is equal to E delta S cos theta. So the unit of delta phi, which is electric flux, is Newton per Coulomb meter square. The next very important law is Gauss law in this first chapter, which is very important, and for 2 mark, you'll have a question like state Gauss law in electrostatics. Then the statement of the Gauss law, which carries 1 mark. The statement of the Gauss law is the total electric flux through a closed surface in an electric field is equal to 1 by epsilon naught times the total charge enclosed by it. To explain this Gauss law, in the explanation, you are going to write the expression. The symbol of flux is phi. Phi is equal to, according to the statement, 1 by epsilon naught times the total charge enclosed by the closed surface, as in this picture. Then you have to explain the symbol, where phi is total electric flux, Q is the net charge enclosed by the surface, and epsilon naught is the permittivity of free space. Now, on this Gauss law, we have the application. The first application is to find the electric field due to an infinitely long, straight, uniformly charged wire using Gauss law. This is a first application of Gauss law. where we need to find the electric field due to infinitely long, straight, uniformly charged wire. So for that, consider here the diagram. This is the wire. Due to this wire, what is the expression for the electric field? We need to find it. We'll start the derivation from the explanation. The explanation is that consider an infinitely long, straight, uniformly charged wire. So as in this picture, and this wire has continuous charge distribution. In continuous charge distribution, we have three types. One of the type is linear charge density, which is represented as lambda. So what is lambda? Linear charge density. How to define linear charge density? Linear charge density is the ratio of charge per unit length. Charge per unit length. This is the definition of linear charge density. Whose SI unit is? The SI unit of linear charge density is Coulomb per meter. Coulomb per meter. Next is the electric field. R is the radius. P is a point at a distance R from the wire, as in this picture. And direction of electric field is radial. You can observe here. Then Gaussian surface. The suitable Gaussian surface to apply the Gauss law is cylindrical Gaussian surface. So, to apply Gauss law, we have to consider a closed surface, which is an imaginary surface. That surface here, it is cylindrical Gaussian surface. And Q is the charge enclosed by the cylinder. The length of the cylinder is L. To find the expression for the electric field, the first step is to calculate the flux through the cylindrical Gaussian surface. So this cylindrical Gaussian surface, let us divide into three parts that are phase 1, phase 2 and the curved surface. So this Gaussian imaginary surface is divided into three parts to calculate the flux through all the three parts. Consider the phase 1. Through this phase 1, let us calculate the total number of electric flux. The flux, according to the definition, it is given by Es cos theta, where E is electric field and S is the area. Theta is the angle between electric field and area. Means here we have to consider the area as vector quantity which has the direction. Then what is the direction of this area? The direction of the area is always normal and outward, and it is represented as n cap. And the direction of electric field is away from the charge. Between these two, what is the angle? Angle is 90 degree. So theta is equal to 90 degree. Cos 90 degree is equal to 0. Therefore, flux through phase 1 is 0. Means there are no number of electric field line passing through that phase. Same way, let us calculate through phase 2. So phi is equal to Es cos theta, and let us find the theta between the electric field and the direction of area. Here the angle is 90 degree. Therefore, theta is equal to 90 degree. Cos 90 degree is equal to 0. Hence, phi is equal to 0 through phase 2. The last part is curved surface. Through curved surface, To calculate the flux, consider the same expression Es cos theta. But in this case, I consider a small portion at point P of this curved surface, and this small portion, in the small portion, let us calculate the number of electric flux. To calculate the number of electric flux, first we have to know the angle between the area and the electric field. The area direction is outward and normal. The electric field direction is in the direction of area. Now both are in same direction. Therefore, angle between them is 0 degree. So theta is equal to 0 degree. Cos 0 degree is equal to 1. And the flux phi is equal to Es. As I have considered a small portion in this curved surface, then I have to represent the area as delta S. Through the small area, the flux is less. So we consider the flux also as delta. Now, to know the total number of flux through this curved surface, we have to integrate. Integrating the delta phi, then integration of E delta S. So integration of delta phi is phi, which is equal to E is the electric field, which is constant throughout the curved surface. Then integrate the delta S, that is the small portion you are going to add it. Integration is nothing but addition. You have to add all the small portion where you have to divide the curved surface into small portion. Then adding the small portion, you will get the total area, that is Es. Phi is equal to Es. Now, we have calculated through all the parts of the Gaussian surface. We will add, or we will find the total electric flux. The total electric flux. The total electric flux through Gaussian surface, phi is equal to, through phase 1, let us mark the phase 1 as phi 1, phase 2 as phi 2, and through the curved surface as 3. So phi 3. Adding all this, you will get the total electric flux through the Gaussian surface. So through phi 1 is 0, through phase 2 is 0, and through curved surface we have Es. So total electric flux is equal to Es, where E is the electric field, S is the area of the Gaussian surface area of Gaussian surface. So what is S value here? The value of S is 2 pi RL. Substituting the value in the flux expression, we have phi is equal to E 2 pi RL, where L is the length of the cylindrical Gaussian surface. So consider this as equation 1. Next, we have to apply the Gauss law. By Gauss law, flux is also given by Q by epsilon naught. Equation 2. Compare the equation 1 and 2. Comparing equation 1 and 2. E 2 pi RL is equal to Q by epsilon naught. The next step is to arrange the expression in terms of E, then you get E is equal to Q by 2 pi RL epsilon naught. Then we will calculate the charge on this wire using the linear charge density. Linear charge density lambda is equal to Q by L. Then the value of Q on the wire is lambda L. Substitute this in the equation 3. Substituting, let us consider this as 4 and 3. Then we have E is equal to lambda L by 2 pi R L epsilon naught, where L gets cancelled. The final expression for the electric field is lambda by 2 pi R epsilon naught. This gives the magnitude, but electric field is a vector quantity. So in vector form, electric field E, vector E is equal to lambda by 2 pi R epsilon naught n cap. The n cap is a unit vector which represents the direction of the electric field. As the direction of electric field is in the direction of n cap, therefore we have to write the positive sign for the n cap. This is the expression for the electric field due to infinitely long uniformly charged wire. In this session, you have learned the electric flux, Gauss law and its application, one of the application. In the next session, let us discuss another 2 applications of Gauss law. Thank you.